Swayam Prabha. Digital India. Educated India.
In this lecture, we'll be discussing the concept of linearization around the equilibrium point. Based on the equilibrium point, we can linearize the nonlinear system and we can get the linear model. In this direction, we'll be taking an example of pendulum system and how we can linearize the pendulum system at the different equilibrium point. Then also we'll try to connect the concept of dynamic stability and static stability to this particular system, and then we'll conclude the lecture. Hello everyone, in this lecture we'll be talking how we can find the equilibrium point of a nonlinear system. So let's take an example of a pendulum system. Example, pendulum system. And let's assume the length of the pendulum is L, suppose this is my starting point and a reference point, and the pendulum is the ball which will rotate in 360-degree rotations. The length of this pendulum system is L, and this is one point where can pendulum stay. There's another point. This is also a pendulum can stay here as it is. But other point it will disturb and it may fall down to this reference point or this point. So now the angular position in this situation, let's assume theta of t. This is my reference point O. And in this condition, let's assume theta equal to 0. And in this condition, theta equal to, let me assume, pi. And this is my reference line, I can say. So this is how the pendulum rotates about the reference point O. The equation of motion, of the pendulum in the absence of the externally applied torque. Why externally applied torque? Because we can assume that total torque being applied is 0. Let's assume it means there is no disturbance or control torque is being applied to the system. So in this case, the equation of motion can be written as L t square theta t by dt square plus g sine theta t equal to 0. So this is very fundamental equation for the pendulum system. And this system is, let me write this equation number 1. This equation number 1 is nonlinear equation. Nonlinear. Due to the sine theta t term, the system is nonlinear. The pendulum system, in this case, the pendulum system can be brought to rest at two positions. The pendulum can be brought to rest at only two positions. One is theta equal to 0 and theta equal to pi. And let's discuss how this theta equal to 0 and theta equal to pi is arrived. Let's find how these points are being derived. These are points actually called equilibrium point. So how it is been derived, let's check. Let's write this equation number one. Let's write the equation number 1 in first order OD. So OD is ordinary differential equation. This is also differential equation. So now we'll write this equation. This is actually second order system. This equation number is second order system. So now we'll write the second order system into two first order systems. So let's denote x1 equal to theta of t and x1 dot equal to, let me write x2, which is theta dot t. And from this, we can write from this two state variable, one is x1, one is x2, we can come up with x1 equal to x2 and x2 dot equal to, we can write minus z by L sine theta of t. And let me write, so why we are converting this second order system to first order ODs? Because to find the equilibrium point, we generally define the system into first order OD. Because the equilibrium point we assume to be constant and the rate of change of that value is assumed to be 0. So now from this system we can write x1 dot equal to f1 x1 x2 and x2 dot equal to f2 x1 x2 and t. So two systems we are coming up which are in first order OD form. From the first equation, x1 dot equal to 0, and from this we get x2 equal to 0 because x1 dot equal to x2, and so x2 equal to 0 we are coming up. And from the second equation, x2 dot equal to, we'll put 0, and from this we can write minus c by L sine theta of t equal to 0, and from this we can write theta of t equal to n pi, and where n equal to 0, 1, 2, something like this. Now for n equal to 1, we have two equilibrium point which are 0, 0 and pi 0. So because here we can come up for n equal to 1, we have x1 equal to, basically this is what? This is actually x1. So x1 equal to pi, and for n equal to 0, also we are having 0, 0. So we are having two equilibrium point. So now what we'll do is, we'll vary here now, we vary theta of t between theta equal to 0 and theta equal to pi. Let us examine the behavior of the system near this equilibrium point, how the system behaves around this equilibrium point. Because if you see the static and dynamic stability we discussed, with stability we define how the system behaves around the equilibrium point. So now if you look at the equation number 1, due to the sine of sine theta, the system become nonlinear, right? So now we'll approximate this sine of theta about the equilibrium point theta equal to 0. So expand sine of theta t about the equilibrium point theta equal to 0 with a small perturbations on the system, how the system behaves around theta equal to 0. We'll check it. So if you extend the sine of theta t using Taylor series expansion, we can write sine theta, theta minus theta cube 3 factorial plus theta 5 factorial and a theta 7 and 7 factorial, something like we'll be moving. So now if we assume the motion of the pendulum theta equal to 0 is considered small angular displacement, if we assume here, or let me write equation number 2, theta in equation number 2 consists of small angular displacement. We can write sine of theta is equivalent to theta, because for small angular displacement these values are very small in magnitude, so we can write sine theta equivalent to theta. So in this condition, equation number 1, in the above condition equation number 1 means our nonlinear equation. This equation number 1 can be written as L d square theta of t dt square plus c theta of t equal to 0. And this is basically second order ODE. And if the equation of, okay, further we can write theta square d square theta of t dt square plus g by L theta of t equal to 0. So this is a simple ordinary differential equation, and we can come up with a solution, because I'm not going to discuss how we can solve it. It's very easy. So because this is a second order system, we'll have two roots, and those are basically complex conjugate roots. And the solution of, let me write this equation number 3 of equation 3, we can write theta of t equal to a1 sine root over g by L t plus a2 cos root over g by L t. So this is the solution of this equation number 3. And let me define this is question number 4. So this is the system, how we get from the equilibrium point theta equal to 0, how the system evolves over time. This is the expression. Now we'll look at the expression for theta equal to pi, how the system equation yields to be. So similarly, let's look sine of theta about the equilibrium point. Theta equal to pi. Now here, if you displace this theta equal to pi, suppose if you displace the body, if you displace this point with some perturbations, let me assume phi. Phi is some angular displacement from the theta equal to pi, if you assume. So let me write, by assuming small angular displacement, denoted by phi from theta equal to pi, we can write phi equal to pi minus theta. This is, we can denote, this is basically the angular displacement phi from the equilibrium point pi. So theta is basically the angular motion, how the pendulum moves in 360 degree. We can write this expression. So now, if you write sine of theta, we can write sine of phi. We can write, because sine pi minus phi equal to sine phi, we can write. And this is also for small angular displacement of phi, we can write phi. Right. This is also we can write. So now what we'll do is, using the above condition, equation 1 can be written as L d square phi of t. Now we are representing the system in terms of pi. Now here pi is constant, so we can write this expression dt square minus g phi of t equal to 0. And from this further we can write d square phi of t dt square minus g by L phi of t equal to 0. Now, if you assume the solution of this expression, let me write, this is equation number 5. The solution, if you want to find a solution of equation number 5, let's substitute phi of t equal to lambda t. And from this, we can write d phi dt equal to lambda t, and t square phi dt square equal to lambda square lambda t. Now substituting these expressions in equation number 5, we can write equation number 6, substituting equation 6 in equation 5 yields, we can write lambda square lambda t minus g by L lambda t equal to 0. And from this we can write lambda square equal to 3 by L, or lambda equal to plus minus c by L. The solution for these roots, there is 2 roots for equation 5. The solution of equation 5 can be written as phi of t c1 e to the power lambda on t plus, because there are 2 roots, you can say lambda 1 plus root over g by L, and lambda 2 minus root over g by L, we can write. So, and c2 we can write c2 e to the power lambda 2t. And this is the solution for the second equation, equation number 5. And if you notice carefully here, it will be minus, sorry. I can write this is, okay, this is fine. Lambda 1 is positive, lambda 2 is negative. So if you look carefully in this this equation number, right, 7. And if you plot this, the response of the respective system, equation number 4 and equation number 7, we can have, if you find the response, this we can get. If you look equation number 7, this is basically one term is positive, one term is negative, lambda 1 and lambda 2. Due to the positive term, suppose this is my positive lambda. In this case, due to the exponential part, the system is diverging with time. But if it is even negative, it may be going to 0. But due to the positive term, the response will diverge over time. So if you assume the system is starting from here, initial conditions, but initial condition system is starting from here, the system will diverge with time. So this is basically equation 7. And I can say system is unstable if it is disturbed from the equilibrium point theta equal to pi. So why it is happening? Because if you go back to our system, if you notice here, with small perturbations on this pendulum, it will fall down. So I can say this equilibrium point is unstable equilibrium point. With a small perturbation, system will not be in the at theta equal to pi, so it will fall down. So this system is, this equation yields to be unstable response. Now, if you look the equation number 7, and if you start from the same initial conditions, the system will evolve like this, something like this. So why it's happening so? Because system, due to the presence of sine cosine terms, system will have the sustained oscillation with same frequency, and here a1 a2 are constant. So we can say that the system is, so equation number 5, we can say stable equilibrium point. Why it is stable? Because system is not diverging with the same magnitude. The system is oscillating, and it will continue like this. And this is how we can define the system stability around the equilibrium point. For the equation 7, I mean the response in the red color, this response system is, due to the equilibrium point is unstable, the system response is unstable. And also in the second case, when equation number 5, in this case, the system is stable. It is sustained oscillation of the same magnitude. Sometimes it is difficult to analyze the system using the above concept, because it is difficult how we can come up with the linear model of the system, which is highly complex. For that case, we can use some standard technique, how we can convert the nonlinear system into linear form. Suppose we have nonlinear system, and we need to convert this nonlinear system into linear form. What you have done in the previous example, if you look the system, equation number 5 and equation number 3, basically this is a linear system. But to come up with this form is quite tedious. So now we'll be using some simple method how we can come up with the linear form if you have the equilibrium points of the nonlinear system. So let's start with the same example. We had theta double dot equal to minus g upon L sine of theta. So here, this is basically nonlinear equation due to the presence of sine theta. And if you can remember that we come up with some state first order, second order, first order systems where we have the change of variables, x1 equal to theta and x2 equal to, we had theta dot. And from these states, we have the system, first order system, x1 dot equal to x2 and x2 dot equal to, we had g of 1L sine of theta, or we can write c by L sine x1. So here, this is also a nonlinear system. This is the second first order ODE, first order ODE, ordinary differential equation, and this system is nonlinear basically because of sine x1 terms exist in the system. Now, if you define a vector, if you define state vector, let me define state vector x, capital X equal to x1 and x2. x1, x2 basically the states in the system. Let me define the equation number 8. And let output be y equal to x1. So here, if you go back that to this equation, here x1 equal to theta. So theta basically evolves over time, how the system evolves with as time proceeds. So here I can say x1 is my output for this pendulum system. And in that case, we can write y equal to g of x. G of x of some function, which is the function of x. And we can write then the system, the pendulum system, we can write in this form equal to f of x and y equal to g of x. So this is we call the nonlinear system, state equation of the nonlinear system. So here we can write where we can write f of x equal to x2 minus z upon L sine x1 and g of x we can write x1. So this is how we define the nonlinear system in this nonlinear state equation. So now this is basically for pendulum system, but in general we can write in general the state space representation of a nonlinear system. We can write x dot equal to f of xu and y equal to g of xu. So here x is the state and u can be any forcing term or control term or any other moment term acting on the system, and where the dimension are f Rn, Rm2, Rn and C Rn, Rm2. So this is, we can come up with some general conclusion of the state equation of a nonlinear system. In the next lecture, we'll continue how we can define a nonlinear system in this form and how we can come up with the linear model of that nonlinear system. This is very easy. If you go through this complete process, it is not that difficult, and we'll be showing the process through an example. So let's stop it here. We'll continue from the next lecture.